Today I'm going to be discussing the origins of algorithmic instabilities and crowdsourced ranking. First, to give some background, our work is inspired by the Music Lab study by SIGCHI et al. In 2006. In this study, they looked at how social influence affects the ranking of songs, how popular songs become. They find, through an independent metric of quality, the best songs and the worst songs were correctly ranked, but mediocre songs were hard to rank. Sometimes they're near the top, sometimes they're near the bottom. And we want to understand why that is. More specifically, our research questions are: how does quality and option appearance jointly impact decisions? When is algorithmic ranking unstable and doesn't reliably identify the best option? And finally, how can we stabilize algorithmic ranking such that the best option is typically ranked first? To answer these questions, we create an experiment with three conditions. In the first condition, subjects are given a question, such as the area ratio of larger and smaller shapes, and asked to guess the right answer. In the second condition, subjects are simply asked to choose the best of two answers visible. And in the third condition, subjects are asked to choose the best of two answers visible, with one answer randomly chosen to be called more popular. In total, there's 1,800 subjects, or about 600 subjects per condition. There are 10 questions per session. And finally, questions were meant to be simple, but with hard answers. To better answer research question 1, the impact of quality and appearance on decision making, we plot the likelihood the best answer is chosen versus the answer quality difference, delta. This metric is defined such that when delta is 0, answers are equally good. When delta is different from 0, either greater than or smaller than 0, the best answer is more obvious. So long as delta is not equal to 0, there's an objectively better answer. In the control condition, we find that when delta is near 0, there's equally likelihood of picking each answer, even though, again, there's an objectively better answer. Moreover, there's little impact of answer order. Whether the answer is ranked first or second doesn't impact the likelihood that the best answer is chosen. And finally, we see good agreement with the model, which is the dashed purple line and the green solid line. In the social influence condition, we see a much stronger preference for the first answer. There's, in other words, a much stronger position bias, as shown with the purple line being much higher than the green line. But moreover, there's still the similar qualitative behavior as in the control condition, including good agreement with the model. Next, to answer research question 2, what creates ranking instability? We plot the phase diagram of ranking stability versus the answer quality of the worst answer on the y-axis and the position bias P on the x-axis. The model predicts instability in ranking by popularity when the position bias is too high, i.e. near 1, and when the answer quality is too ambiguous. For example, the worst answer is near the quality of the best answer, which is when the A-worst is near 0. Instead, answers are ranked correctly when the worst answer is very bad or when position bias is low. This is in qualitative agreement with SIGCHI et al., and therefore explains the paradox of popularity, in which mediocre answers vary widely in popularity, but a good answer still float to the top. Finally, to answer research question 3, stabilizing algorithmic ranking, we show in the right plots that simulations demonstrate instability of ranking popularity and recency ranking, i.e. ranking by the last vote. It also shows that crowdsourcing breaks down if the good answer has fewer votes, for example, arrives later. To address these issues, in the black lines on the right, we create this algorithm called Raissa, rectifying algorithmic instabilities in crowdsourced ranking. This method is guaranteed to be the best method if data matches the model, and it clearly shows advances over the other methods, other baselines. So in conclusion, for the first time we modeled the relationship between option quality, option presentation, and decision accuracy. We find that answer quality helps explain algorithmic ranking instability, and we create a simple algorithm with theoretical guarantees to best rank answers. The implications of our work is threefold. First off, crowdsourcing is messy. Our model shows that roughly 20% of votes are random, and moreover, random votes, along with position bias, help create ranking instability. To reduce ranking instability and to improve crowdsourcing, designers must reduce or control position bias, especially with the first few votes given to each answer. With that, I would like to thank my colleagues, Ted Hogg, Raissa, Kristina Lerman, and Marton Posfai, as well as our funding sources, the U.S. Army Research Office and DARPA. And I will thank you for your time.